So earlier we had this formula that would help us figure out the slope of the tangent line of a function. It was the limit as x approaches a of f of x minus f of a over x minus a. We know that this is rise over run. I want to give you another formula that is equivalent to this, but it just requires looking at the drawing a little differently, looking at the diagram a little bit differently. In fact, I'm going to pop up a new diagram so that we can take a look. All right, so this is effectively the same diagram. We've got the same graph of a function. We've got those points P and Q that we're using to get the secant line, and the P is kind of our base point. That's where we're going to want the tangent line. But I'm going to rename things. Instead of calling this other x value x, which is not really the nicest thing to do because x is just supposed to represent any variable, and so we don't want it to represent a specific point. We're going to redefine things, and what we're going to say is this is a point that we get if we start at A and we move h units to the right. So we're just going to define this by how far away it is from our starting point A. So here our points are going to be a and a plus h, and then that means that the function values of these are going to be f of a plus h and f of a. And so when we take the difference to get the rise, it's going to be this difference, f of a plus h minus f of a. And then the run is going to be this length here, which is going to be h. And this allows us to rewrite the slope formula in a slightly different way. It's going to be the limit, and in this case, it's going to be the limit as h approaches 0, because we want this distance to get smaller and smaller and smaller as this point moves to the left, as q approaches p. H is going to go to 0, so it's going to be the limit as h approaches 0 of the rise, which is f of a plus h minus f of a, over the run, which in this case is just h. And so this is another formula that we can use to figure out the slope of the tangent line. We can use either one of these formulas. They are equivalent. They'll give us slightly different algebra in the middle as we solve problems, but in the end, we will end up getting the same answer. And this is such an important quantity because it gives us the slope of the tangent line, because it gives us instantaneous velocity. We actually have a name for this, and we have special notation, and that's what I want to go over now. We call this value the derivative of a function, f, at a number a, denoted by, and we call that f prime of a. This symbol we read as prime. So we either say the derivative of f at a or f prime of a. And this is defined to be that limit as h approaches 0 of f of a plus h minus f of a over h, all if that limit exists. This is such an important thing moving forward because it gives us instantaneous velocity, because it gives us slope of tangent lines. It's also going to give us other things in other contexts. So important that we have given it a name. We call it the derivative. So I want to do one problem together, actually referring to this as the derivative so that we are getting comfortable with this notation and with calling this the derivative. So what we're going to do is we're going to find the derivative of the function f of x equals x squared minus 8x plus 9 at the value x equals a. We could pick a number for a. We could figure out the derivative when x equals 3, or when x equals 12, or when x equals 26. But what we're going to do is we're just going to let x be a, and then the value of the derivative we're going to get is going to be in terms of a. And then if we want to know what happens when a is 3, or a is 26, or a is 100, we can just plug that in, and we don't have to go through the process of evaluating a new limit each time. So let's start working on this. We've got f prime of a, That means the derivative of f at a, it is the limit as h approaches 0 of, we know that's going to be f of a plus h minus f of a. So we have to start by evaluating this function at a plus h. So that's going to be a plus h squared minus 8 times a plus h. Wherever there's an x, I'm plugging in a plus h, plus 9, minus our function at a. And if we plug in a here, that's just going to be a squared minus 8a plus 9. I need to put that all in parentheses because we're subtracting this whole quantity. We're going to have to distribute that negative in a moment. And then this is all over h, at least the denominator is simple. So we're going to have to do some algebra with the numerator here. Just writing my limit again. We can FOIL out a plus h squared. We've seen that before. It's a squared plus 2ah plus h squared. And then when we distribute that negative 8 to the a and the h, that gives us minus 8a minus 8h, and then plus 9. And then when we distribute that subtraction to each of the terms in the second polynomial, that's going to be a minus a squared plus 8a and then minus 9 all over h. Now we need to see what we can simplify. There's a lot of terms that we can cancel. I see a positive a squared and a negative a squared. I see a negative 8a and a positive 8a. I see a positive 9 and a negative 9. And I think that's all that we can cancel. Let's figure out what that leaves us with. So we've got the limit as h approaches 0. In the numerator, we've got 2ah plus h squared minus 8h. I think everything else is canceled, all divided by h. And we're really lucky because all of those terms can be divided by h. So when we do that division, 2ah over h is just 2a. And then plus h squared divided by h is h. And then minus 8h divided by h is just 8. And we need to take the limit of this as h approaches 0. We can use direct substitution here. That h term goes away, and we've got 2a minus 8. And this is super nifty because we can plug this in for any value of a for our function and figure out the slope of the tangent line there. So if we wanted to know a bunch of different tangent lines, we don't have to go through and do a whole limit every time. We can just plug in whichever x value we're looking at for a, and that gives us the slope right away.